one more detailed calculation here for the SVD business. This is going to be another 2 by 2. It will have full rank 2. So we're going to have row space is 2-dimensional, column space is 2-dimensional. The null spaces will be 0-dimensional, right? There'll be nothing in them, as in 0. And but we'll see this kind of flipping rotation story that SVD brings us, right? So here it is. I'm going to work through this pretty methodically. So it's a good example. So we want to unpack this funny looking thing here. So it's not as clear as how this might work as the previous example, but so steady stuff. So we first of all, right, so 1, we diagonalize A transpose A. Right, now look at, in this one we'll look at AA transpose as well, just to fill in some things. All right, so first thing, let's find what this is. So A transpose A is equal to 1/5, and then we take this transpose 11, 10, 5, 1/5, 2, 11. You could just be quiet, monks. 10, 5. All right, so we're just going to get this thing to work. So there's an extra little sneaky monk trick that we'll bring in here. So this is a funny looking business, right? So we have the 1/25 at the front. We have 104 here. Yep, and then 22 plus 50, so it's going to be 72. And then we should get the same thing here again, 22 plus 50, 72. Symmetric, right? And the last thing is 121 plus 26, right? So 146. So this one's a bit of a funny one, all right? Symmetric. As always, guaranteed. Doesn't matter if A is rectangular. It's a beautiful, simple little proof. All right. Okay, this is a funny looking thing. We can factor out just a 2 really, so let's take that out. So there's a 52, 36, 36, 73. So we're going to find the eigenvalues for this guy. So interlude is a sneaky monk trick. All right, number 731. Right, there are always more sneaky monk tricks. So if we have a matrix that has some eigenvalue and eigenvector, and then we have a multiple of that matrix, then we just multiply the eigenvalue. Same eigenvector. Okay, so let's say we have, let's call it B, BV equals lambda V, then we can multiply both by a constant, both sides, C lambda V, which gives us that, we could call this B prime. This is some new matrix. V equals C lambda V. So that is to say, if I'm getting this in the right box, so if, that was weird, right? So if, okay, if V is an eigenvector of B with eigenvalue lambda, then it's also an eigenvector of CB, right? That should be an, I guess, is an eigenvector. Yes, is an eigenvector of CB with eigenvalue, we just multiply. C times lambda. So what we'll do is we'll ignore this piece at the front, right, the 2/25. So so we're just going to find, okay, so we're going to find lambdas for just this thing here, which is bad enough looking by itself, but we'll simplify things a little bit. this is a bit of a mess, right? And think nothing nice will come out of this. But the truth is, because I made this with u, sigma, and v, right? I chose them and made them simple. A is whatever it is. Right, so we're unpacking something here. Okay, so we'll do this, right? Finding eigenvalues, we know all about it, right? So we're going to solve. So we solve determinant, so it's going to be 52 minus lambda, right? Solve the determinant of A minus lambda times the identity equal to 0. Well, that's the general statement. We're actually doing, of course, in this particular case, A transpose A. So 52 minus lambda, there's a 73 minus lambda, and then 36 and 36. So we're going to set that to 0. So let's work through this. All right, so 52 minus lambda, 73 minus lambda, minus 36, all squared. So what is that? So we end up with 52 times 73. So we'll get that right. So there's going to be a 3,500. There's going to be a 6. And then, 296. Right. Right. So 3,796. Yep. That's that piece. Right, and then we get the we'll get a plus lambda squared, and then we're going to add these two pieces together, right? So there's going to be minus 125 times lambda, and then minus 36 squared. So it's 1,296. Yeah. Okay, so that's good. So we'll rearrange things a little bit. Lambda squared. Minus 125 lambda, then these two couple together, and look at that, very nice, 2,500. Now we need to factor this, and you can see however you want to do that sort of thing, but this is 25 plus 100, so that looks pretty good. So we'd end up with lambda minus 25, lambda minus 100. Mm-hmm. So we're actually not solving. This is not quite A transpose A, right? This is just we have to multiply whatever we get out by 25 over 2. So this gives us lambda 1 equals 100. Put them in order of size. And then we have to multiply by 2 over 25. And this gives us lambda 1, the proper lambda 1 is 8. Yep. And I've left off a 2 there, so that's a 25. And lambda 2 equals 2. These are our sigma values squared, right? So this is, which is equal to sigma 1 squared, equal to sigma 2 squared. That gives us sigma 1 equals the square root of 8. I'll just leave it like that. And sigma 2 is the square root of 2. Okay, so that was fun. Always fun. So we're there. Now we have to find the eigenvectors. And we can find the eigenvectors for... Right, it's the same eigenvectors, right? So we can just find them for this story here. Okay, we don't have to worry about that. Okay, so lambda, so, right. I know I'm calling them lambda 1. So this is lambda 1, okay, yeah. This is, right, this is for A transpose A, and this is for, let's make it clear, this is for, it'd be 25 over 2 times A transpose A. Right, we've removed the prefactor, okay? Right, we're going to keep fighting. Okay, so we'll find, we can use, yeah, okay, good. Okay, so lambda 1 equals 8. If we put all of that in, right, then we'll see that we'll have, right, it was really 100 and then a 2/25. So we had all those pieces. So we'd have 2/25 at the front. We're subtracting 100 off here, right back up here and here. So we get a 48. 48. We get a 36. That was always there. 36 and 73 minus 100. Of course, it's minus 48. 73 minus 100 is minus 27. We're solving this problem. And as always, there should be multiples of each other. We can see there's a 4:3 ratio, 4:3 ratio for each piece. So this gives us V1. We'll normalize it. I have trouble when it's over here. Right, equals 3 and 4. And so 3 squared plus 4 squared is 25. Square root of that, so 1/5. So that's very sneaky. So V1 has a nice form. How about that? All right, lambda 2 equals 2. And if we go through and put everything in, we're trying to solve the null space equation, right? So this is really, let me write in blue here. This is A transpose A minus lambda I times V equals 0. That's what we're doing here and here. Right, solve these. Normal stuff. Takes a little while, but once we've got, we're nearly there. We're nearly there. Okay, let's go back. So 52 minus, in this case, 25. So it looks like a 27. And then a 36 here, and this is a 36 still. And then we have 73 minus 25, which is 48. Okay, so again, there's that 3 to 4 ratio. We're solving this null space equation. You can do row reduction. We can see it straight away though for 2x2s. 1/5. Yeah, and we'll say this is minus 4/3 because that's going to, if we have V1 here, V2 will be here, and we like that. Okay, but we have a somewhat free choice. So could choose, right, once it's a unit vector, the length doesn't, right, we have no flexibility in length, but we could choose the opposite. So this is just a note. Okay, we did not. Okay, pretty good. So now we have V. There's a 5th at the front, so I'll pull it out the front. That's a normalization. It's going to be 3 and 4, and then minus 4 and 3. And sigma, that's fun. Sigma is the square root of 8 and the square root of 2. So these are the natural stretching factors in here. It doesn't look like it, right? But this matrix here, sorry, that's the wrong one. This matrix up here has these natural, these are its natural pieces. These are its preferred directions for row space. It really likes them, so let's blob this up. And yeah, built somewhere sitting inside this matrix, not obvious. Same with eigenvalues and pivots and so on. Square root of 8 and square root of 2. That is really what this thing is about. You could say that this matrix encodes this more, a verbal description, right? Take this direction, stretch it by this much, take by square root of 8, take another direction, stretch it by square root of 2, and so on. And then point them in these new directions, which we haven't figured out yet. And this is the encoding of that thing, right? Say, I want to stretch this much and stretch this much. Well, we can create the matrix version of it. So that's all rather delicious. And so now we find, I know you're excited. Yeah, it's very nice. So now find the u's. Right. Well, we've just got two of them, so let's just say u1 and u2. And I guess I wanted to cover both of the possibilities. So first of all, there's u I equals 1 over sigma I a times vi. And this is kind of generally the best way, right? Right. So this is the best way. It's going to be simple to do. So for instance, the first one, u1, it's 1 over the square root of 8. That's our sigma value. And then we have this 1 over 5, 2, 11, 10, and 5. Let me not get that wrong. This is A. And then we had 1 over 5, 4 and 3 and 4, 3 and 4. Right, that's going to be u1. So we multiply this out, we will get a unit vector, which is surprising. That's always kind of a nice thing to see here. So let's collect pieces. There's a 1 over 25, and we're just going to multiply this out, right? So 211 dotted with, or inner product with 3, 4. So it's going to be 6 plus 44, 50, very suspicious. 30 plus 20, another 50. So we've got 1 over root 8. What happened there? 1 over root 8, and then 2, 2. Of course, this is 1 over 2 root 2, so that cancels, and it's 1, 1. So, unit vector, right? Guaranteed. So many things are guaranteed. But it's very nice to work through. You should see that at the end you get a normalized unit vector. So that's u1, u2. Again, so square, it's going to be 1 over root 2. We're going to have a again, 2, 11, 10, 5. And then the second v, 4, 3, and we put a minus sign here, so we multiply through. We're going to get 1 over root 2, and then this 1 over 25 again. Minus 8, plus 33, so that's 25. And then minus 40, plus 15, so it's minus 25. Very sneakily, things fall through very nicely, and we end up with 1 minus 1. Okay, so again, unit vectors, let me pluralize that, unit vectors are guaranteed. So we're done. So now we have u. U equals 1 over root 2, and we just stack them next to each other, 1, 1, and then 1 minus 1. Okay? So, just to fill out everything, so we could also diagonalize A transpose. Right, so let's do that. Let's do that. So it's going to be, we compute, right, this is to find the u's. It is a remarkable thing. So AA transpose, so it's 1/5, 2, 11, 10, 5, and then we have to flip it, 1, 5. So there's 2, 5, and they swap. Let's see what this thing is. 1/25. So we're going to have a 4 plus 121, so it's 125. And then 20 plus 55, so it's 75. Has to be symmetric, so we can just write it down, but we should check. So the 20, yes, yep. And then 100 and 125. Right? Lots of things divide through. So this one turns out to be much simpler than A transpose A. 5, right? 3, 3, and 5. So if you go through, so we'd work through, we'd solve it, so we would find lambda 1 equals 8, lambda 2 equals 2, right? You can see how that's going to work. If you subtract off, you get minus 3, 3, and 3 minus 3, or 3, 3, and 3, 3. And u1 would be 1 over root 2. Now here we wouldn't be sure about it actually. We'd have plus or minus that. And u2 equals 1 over root 2 plus or minus, and we'd have 1 minus 1. So we're not sure about the signs. About signs. So we'd still have to compute this business here. So essentially, yeah, 1 over sigma I ui equals 1 over sigma I A times vi. Right? So that's a good thing to understand. It's important to be able to see that it works from both sides. Everything pops out. But ultimately, we're going to have to use this method whichever way we do it. Okay, good. So this is sort of an aside here. Well, I don't need that. Okay, so overall, we have A equals 1/5, 2, 11, 10, and 5 equals all these pieces. So there's going to be a 1 over root 2, 1, 1, minus, it's not there actually, 1 minus 1. And then we have a square root of 8, square root of 2, and then 1/5. This will be 3, 4, and then minus 4, 3. Let's do it like that. I think that is good. Yep. Let's just indicate what these are. So this is, of course, U. This is sigma. And then this is U V transpose. Right, so this is the best basis for row space. This is the best basis for column space. And this is the connective piece between the two. So let's draw a picture, and then I think we're good. Yeah. Okay, so again, over here we've got x1 and x2. This is where the x's live, the y's live over here. So this is, if you like, so we're ax equals b. It's our ax equals b kind of problem that we're thinking about, or we're trying to solve that problem. Or we could just think about y equals a times x. Different things that we're playing around with. Okay, so once again we'd have a unit circle. Pretty bad unit circle, but this is okay. So this is 1, 1, and we start with 3, 4, and then minus 4, 3. So 3, 4 is here. Here's 3, 4.
I just dropped my cactus on my desk, and now there's a lot of dirt on my desk, and my finger just got a lot of cactus bites in them, and it really hurts.
Okay, can you go and see Mommy? You'll have to go and see Mommy. All right. I want you to just go and pull out the little pieces, all right? Okay? Get some tweezers and pull out the little pieces. It's all you're going to do. You're going to pull out cactus. You can do it. All right. Okay, and we're back. The patient seems to have survived. Interesting. All right, so we have this little story here, right? So I'm just trying to sketch out what things look like for this particular A. So this was V1. V2 is over here. It is at right angles because of the magic of symmetric matrices, V2. So it's 1 over 5 minus 4, 3, right angles. This is actually really, both of these make up row space, right? So they're a basis for row space. Right, so let's add some pieces over here. This is R2, which is Rn in this case. It's where the x's are here, all those good guys. And so row space is equal to R squared, and the null space of A in this case is just 0. Right, row space. So we know this whole plane, right? The whole plane gets mapped to the whole plane. What SVD is helping us with here is the details of, for this particular matrix, what's going on when this map occurs. So this is A equals, I should put it in here, so this is A equal to 1 over 5, let's make sure I don't get this right, 2, 11, 10, and 5. Right, so this is our A. So inside this A, it has these nice 2 eigenvectors for row space. And then it had these other ones, which we've seen a million times, but this kind of thing. So maybe this one and this one. So we've got another unit circle over here. So this is 1 over root 2. It's 1, 1. And you know that is not pointing in that direction, actually. This is in another direction. Right? We like it when it points in that direction, but that's not what's going on. So this is U2, and this is U1. I guess I should say, so there's an unfortunate thing. The V's are on the left-hand side of this page, and the U's are on the right-hand side of this page. But when we write U sigma V, they're in order. It is unfortunate. This is really wrong, actually, because the V's are the first thing that act. So I'm just going to put this in a corner. So to sort of note U sigma V transpose. So alphabetic order. You know, U then V, right? But so wrong in terms of wrong order of operations. So that's a bit confusing. The V's are the things we start with, they go to the U's. But it looks better when we write it down like this. That's unfortunate. Just like left null spaces on the right-hand side of the page. All right. Although maybe this is worse. So we're going to send, we understand now that these vectors over here, this orthogonal basis for R2 gets sent to this orthogonal basis over here, in again in R2. But right, I mean, we were happy with I hat j hat, but this is the right basis to start with, and this is the right basis to end up with. So what happens when we map these two pieces? Maybe I'll use a gray. So 3, 4 goes to 1, 1. Right, so that happens. So square root of 8. It's not right, but so this is A times V1 equals the square root of 8 times U1. And at the risk of making a horrible mess, that's not right. So let's map it to about here. So this is A times V2 equals square root of 2 times U2. So what A wants to do is to take this, it likes this direction. Sorry, let's get this right. So it likes this axis here. It wants to take it over to here, or it does, and stretches that one. And then at the same time, it likes to take, not likes, it does it. It takes this axis, maps it over to here, and stretches as well, but by less. Okay, so the thing to draw here to get this right, let me make a bigger plot. There's a unit circle, and it's mapping it to an ellipse. Okay, let's just get this right. It's not going to be a great drawing. Okay, so fine. Ugh, having trouble. So circle to ellipse. So SVD. So this is just a little side note here. I've got my big one on. So the big deal, perhaps here, to see. Big deal. Circle goes to an ellipse. Right, we pick your magic circle up, going over, stretching this way. You have to flip it, and so on. And then generalize dimensions. So that's very, very important. That's a big deal here. And then I want to add one more piece. Right, I'll add one more piece here. So let me get another thing and put it here. Okay. So we're going to have one last statement about all of this. This is episode 24. See page 3. And episode 24. See page 4. Right. So the last thing to say about all of this is that A equals U sigma V transpose. So what happens when we multiply, right? So this is how Y equals AX works. Said it before, we'll do it again. So this is 1, 2, and then 3. So this is change from change X's representation, right? So we're multiplying X, right? From standard basis, standard to the V basis, right? We're just changing the way it's represented. We're not, right? And then the sigmas, so the work, does the work of A, for A, and it's going to have the sigmas, so it's going to be either stretching or shrinking, right? Stretch, shrink by the sigma I factors in R dimensions. Right, so it's an R-dimensional subspace, column space, and row space. And then U will change it back to the basis, right? And so encoded in U is all the flip, the flipping and rotations and so on. That's all encoded in these different bases, right? So this is a change back to change from U to standard basis. right? And those bases encode the flipping and all these sorts of things. Yeah. All right, so that's enough, I think. So this is a nice big example, something you want to maybe work through again, understand it. But this little matrix here turns out to be, to have a really clear story, but we have to dig into it and dig into it. And this works for arbitrarily large matrices, it works for rectangular matrices, and beautiful story. Okay, so that's going to be the end of it. There may be a little bit of this surgery added to this video, but we are very much getting to the end of what has been a beautiful experience, I'm sure. So what did you do? You just grabbed a whole handful of...
No, I was watering my cactus and I was trying to put it back down on my desk.
And it tipped?
But I dropped it and now there's some dirt on my desk and like a lot of cactus stuff on my fingers. And my cactus fell out of the pot.
Sounds like you need to wear gloves when you deal with your cactus friend.
There's still a lot in my pinky.
It's a nasty cactus.
Yeah.
You got attacked by a cactus.
Yeah. And Pratchett's hiding under my bed. He's been hiding under my bed a lot today.
What do you think's going on with him?
I don't know. I think he likes it under my bed.
Oh.
Also because I kicked him off from on top of my bed because I had to make my bed. There's still a lot in there. Like, it stings.
Well, we're in trouble.
They're like all in there. Do I have to get finger surgery?
Why would you need surgery?
To get the little cactus things out.
Well, that's what we're doing.
Yeah,
Right? We're just pulling all these pieces out.
there's still one right in there. That little... Ow.
There?
You just like pushed one in. Ow. I think there's one right there. Right. No, right? Yeah. I'm never gonna get a cactus again. Ow!
Okay.
I'll just get succulents.
So funny.
Ow.
I think you need to wear gloves when dealing
Well,
with
also
your...
my cactus like tipped out of the pot.
Maybe a visor? Some special overalls?
Mama won't get me overalls.
Maybe a hazmat suit when you do it? How's that feel? A lot of them out?
Most of them. There's still one right there.
Got it, yeah?
No. It's still there. And there's one right there. Right there. On my pinky.
On your pinky?
Right there. Right there. No, you got the wrong spot. No, wrong spot. No, it's right there. There. No, you're like right in this, right here.
Yeah?
Right there.
It's hard to see because the light's doing something different for me. Where? Tell me which way.
A little bit.
Oh,
this
no, I
way.
can see it. Wow,
Yay.
they're tiny, aren't they? Okay. Ready? What do you think?
There's still one. It's really, really tiny. I need to...
Can you get it?
I think I might have pushed it in.
The one that you try to get out.
That little black speck thing.
I'm going to try again.
There's also... I can't tell if that...
If you can't really feel them anymore, then it doesn't...
Oh, there's one right there, I think. Yeah.
I think you're okay. All right?
Okay, thank you. Now I have to go clean up my desk.
Okay.
Throw away
All right.
this.
Don't throw away your cactus.
It fell out of the pot.
Well, get some gloves and put it back in. Just because it attacked you